All right, so back again for some more centripetal motion problems. Awesome stuff. Just as a reminder, right, the centripetal centripetal acceleration equation is this guy right here, right? So centripetal acceleration is the perpendicular component of the acceleration to your velocity vector, right? So notice this diagram over here. It's the part of your net acceleration that's perpendicular to your velocity that allows you to travel on sort of circular trajectories, right? So that part of your acceleration has this relationship to it, and it relates the speed and the radius and the acceleration all together in one equation. So we're going to use that in these problems. So last class we did this problem. Now, there was one aspect of this problem that a student in block 5 pointed out to me that I didn't recognize in the moment while I was going through it with block 1. But if you think about it, the addition of this normal force and this force of gravity, if you add those together and you look at what does the net force look like, it actually looks like this. I think for the other block, we had just drawn it completely horizontally, which actually doesn't make sense, right? So it's actually this slanted, oh, why did it go over there? It's actually this slanted blue arrow, right? And so there was actually a few more steps to be taken, right? It wasn't just enough to find the net force. So what you essentially had to do is draw this triangle, right? Where this horizontal component is the actual force we see in this diagram that allows you to travel on this circular path, right? But that's not the same as the net force. And so using some trigonometry, you have to find the centripetal force in terms of the net force. And so you end up getting something like this. I think in block 1, we might have had maybe this term, and we didn't have this cosine component. We caught it in block 5, didn't catch it in block 1. So these problems are tricky. You got to be very careful. So anyway, let's move on to this one. And one thing I want to point out about this one is what they're ultimately asking for is they say find the period of the airplane's motion. So period, I don't know that we've talked about it in class. This is the time it takes, oh my gosh, I can't write today, for one revolution. That's really all we need to know for this problem. So typically the symbol for period is capital T. And we're going to go through some formulas later that help you like quantify it for different situations. But really, if we just know this as the definition of what a period is, we can figure it out intuitively for this problem. So let's read it first and just go from there. So you have probably seen toy airplanes flying in a circle at the end of a string. Once the plane reaches a constant speed, it does not move up or down, just along in a horizontal circle. Suppose you have an airplane attached to the end of a 46 centimeter string, which makes a 25-degree angle relative to the horizontal while the airplane is flying. A scale at the top of the string measures the force that the string exerts on the airplane. Okay, that's neat. Find the period of the airplane's motion. Okay, so definitely the first thing is this picture right here was actually not included with the question. This is actually part of, like, starting here, this is actually a snapshot of the first steps in the solution. So this is straight from the textbook itself. This was a worked example in the textbook, but we want to rework it so we can understand it. So you would have to come up with this kind of picture. It's kind of a complicated picture, but anyway, so here's our airplane. And a good place to start when you don't know at all what you're going to do is start with the free body diagram. All right, start with that. So let's think about this airplane as a point mass and what forces are acting on this airplane. We're ignoring air resistance. it sounds like, right? Otherwise, this problem will be a lot more complicated. So assuming air resistance is negligible, right? What forces are acting on the airplane? Well, that's, why did it erase that? So that's gravity, force of gravity. And then we have the tension force. And we actually know exactly how big it's supposed to be, right? So let me kind of draw how big the tension force should be according to my force of gravity, right? Why am I making the tension force this long? Well, it's because this y component of the tension force, we could call that Ty, should be the same magnitude as the force of gravity down there, right? Those are the components that cancel. And so what you have here is when you add those two forces up, right, this purple arrow represents not only just the net force, but you could also just think of it as Tx, right? This is the x component of tension, right? But because we're moving in a circle, this is my centripetal force, right? So the net force is completely pointing towards the center of rotation, right? It's not causing any sort of speeding up or slowing down of the airplane. So that makes the problem a lot simpler because they told us this, right? They told us the plane reaches a constant speed, right? So there's no way the acceleration could not be just the net acceleration or the net force could be pointing away from the center, right? So that's exactly what we get, which is great. Now, depending on which class you're in, you may have seen me talk about centripetal force, right? So we definitely talked about centripetal acceleration and found that equation. Centripetal force, even though on your green sheet there's not a place for this formula, it's actually a really good formula to know. So it's just like the centripetal acceleration formula, except you have multiplied by mass, right? Because the idea is that force, centripetal force, would be mass times centripetal acceleration, right? That essentially, that's what this centripetal force is, mass times centripetal acceleration. And so you just multiply by mass for this other formula. Now, you can get by with only knowing this formula, that's fine. But it's also nice to know this as well, just in the back of your pocket. So anyway, point is, I know my centripetal force in general is Tx, what we're calling Tx. The mass, do they give us the mass? Let's see. Okay, they do not. They do not. And V, did they give us V? I don't think they give that. They don't give us that either. Okay, great. All right, do they give us R? Well, they give us the length of the string, so we could find R. Okay, so that's one thing. And also, we could use some angles to find, we could actually find Tx directly as well. So let's maybe start with R. So R, let me do this in green maybe. So R is this length. And we could kind of set up this triangle here, right? So like this right here, because we know the length of the string, the hypotenuse, right? We also know that this angle right here, I don't know if y'all can see that, is going to be 25 degrees also, right? That's the alternate interior angle theorem from geometry. It tells us those angles are the same. So by setting up this triangle, I know that cosine of 25 degrees is going to equal my adjacent side, which is R, over the length of the string, which is 46 centimeters. So I'll write it as 0.46. And I can solve for R. So R is approximately 0.46 times cosine of 25 degrees. Okay, I might save the calculations for the very end, so I'm actually just going to put this right here. because I think we're going to see something really nice happen. Let's go ahead and find the tension force, right? So Tx. So how can we find Tx based on what we know about the force interactions here? Well, we pointed out earlier that Ty and force of gravity should be equal and opposite, right? So that's going to give us a relationship that we can use to find the overall tension or Tx, right? So we pointed out Ty is equal and opposite, or I guess one way to say it would be like Ty minus Fg should be equal to 0, right? The sum of the forces in the y direction, that's essentially what I'm doing here. Sum of the forces in the y direction should equal 0 because there's no acceleration in the y direction. So we know this is true. So that means Ty equals Fg, and Fg is nothing more than just mg, right? And so when I go back here, I can fill in my diagram, Ty equals mg. So if I know Ty and I want to find Tx, how about I use tangent? Right? So I can use this fact to say, okay, tangent of 25 degrees equals opposite over adjacent. Right? So mg over Tx. Cool. And Tx, if you see it over here, right, that's my centripetal. That's going to go in this equation. So I want to isolate it, right? So if I solve this for Tx, I get Tx equals mg divided by tangent 25 degrees. Okay, so let me put that in. Let's update our formula over here. All right, so we have mg divided by tangent of 25 degrees equals mv squared divided by 0.46 cosine 25 degrees. Okay, you might be wondering, well, hang on, how are we going to get the period from this? Don't worry, right? If we can find that speed, that is sort of the key to this problem. So notice how the m's cancel out. It's awesome. Super awesome, right? So now I can solve for v in terms of everything else. And if you do that, do some algebra work here, right? So I'm going to, just to save time, I'm going to jump through some of these steps here, but you should get basically g times 0.46 cosine of 25 degrees divided by tangent 25 degrees, all inside of a big old square root. Yeah, that should be right. And, there might be another way to get this. I see these trig functions on top of each other. Maybe there's another way to think about what's going on here that I'm not picking up on. But, this is just one way to do the problem. There might be multiple ways. Let's go ahead and get the numerical answer here. So, let me get the keyboard up and running. Okay, so square root. I'm going to use 9.8 for g times 0.46 times cosine of 25 divided by tangent of 25. And double check that we are in degree mode. Yes, we are. So I'm getting a speed of about 2.96 meters per... Oh, wait a second. Is this in meters per second? Yes, it is, because we converted the 46 centimeters to meters. I did it so naturally, I didn't even remember that I did it. Right, so this is the speed of the plane. Cool. But Mr. McMahon, they wanted the period, not the speed. Well, we can use the speed, my friend, because notice, for one revolution, we can look at the circumference, the distance traveled along this circular trajectory, divide that by the speed, or maybe let me put it another way, right? Speed is distance over time. So we can definitely rearrange this to be time equals distance over velocity, right? Or in other words, we should really use capital T, right? So the period would equal the distance, which is the circumference of the path, right, divided by the speed, right? So this is what I was trying to get at. If we can find V, we can find the period, right? And we know the radius, right? We found that earlier. Well, you know what? We didn't calculate it, though. Let's go ahead and calculate that. Dun, 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 dun. So we do that over here. 0.46 cosine 25. So yeah, we're getting 0.42, let's say, meters. 42 centimeters, 0.42 meters. Okay, so the period we're finally looking for here. The period would equal the circumference over the speed. Right? That's how much distance the plane is actually traveling. So that would be 2 pi times 0.42. And then we would divide by our speed, that 2.96 quantity. Right? Notice how we get meters up top, and then down here we have meters per second. So meters divided by meters per second gives you seconds. And so we get the units that we expect, and let's see what we get. 2 pi times 0.42 divided by 2.96. 2 pi times 0.42. Yeah. Okay, so the period, it looks like, is 0.89 seconds. Final answer. There we go. Nice. That seems pretty realistic to me. I don't know about you. Now, one thing I have a question about is why did they even tell us about this spring sense or force sensor thing if we never got the measurement of the force in the first place? Kind of a weird detail, right? So they totally just threw in a complete distractor that has nothing to do with anything. Like, they don't tell you how much the scale measures. Why was that there? I don't understand. I don't. So be careful, right? Not all information is actually relevant or important. Anyway, that's a really neat problem. I like that problem. And I've definitely seen some AP Classroom problems that are modeled based on situations like this. So just knowing how to sort of break up your net force, look at the centripetal component, right? Setting up this equation here, or this one. You could also just use this one, right? Because notice how the mass disappeared regardless. So there was probably a way to use this that I didn't pick up on. Okay, let's try this one. Josh drives his car at a constant 12 meters per second speed over a bridge whose shape is bowed in the vertical arc of a circle. Find the direction and magnitude of the force exerted by the car seat on Josh as he passes the top of the 30-meter radius arc. Okay, his mass is 60 kilograms. Cool. Okay, where should we begin? Where we always begin. Free body diagram. Yes. FBD. Start with it. Make it foolproof, right? So, Josh. What does Josh experience? What forces? Well, he experiences a force of gravity. Yeah. So let's call that force of gravity. And then the seat underneath his butt pushes him up. But intuitively, we know, right, there's a net acceleration pointed down, right, towards the center of the hill. So we know whatever this normal force is smaller. Should be smaller than the force of gravity. Okay. So what do we do with that? Well, the net force then would be pointed kind of down like this. Right? This would be F net, which is our centripetal force in this case. Right? So remember, the centripetal force is not some special kind of force. It's just talking about when your net force is helping you turn. Right? So, and we have this nice little mathematical relationship, right? So Fc, the centripetal force, equals mass times velocity squared over r, right? So net force. Well, we can break this up into force of, the normal force from the seat minus the force of gravity pulling him down. This should be equal to mv squared over r. Okay, interesting. So we have the 30-meter radius arc, that's our r. We have the mass, we'll see if that's super important. And we also have the speed, v. Let me first simplify one more thing. So we can write the force of gravity as mg, right? And the reason I do that is because it looks like I could divide both sides by m, right? And so these two m's will cancel. This m will divide through by both of them, right? But it'll cancel in the second case. So I get the normal force divided by m minus g equals v squared over r. Interesting. If we're trying to find the direction and the magnitude of the force exerted by the car seat on Josh, that is the normal force. Let's go ahead and solve that. All right, let's solve for the normal force. So we get, add the g over, and we get this. It's interesting. Okay, and then multiplied by m. So the normal force would be m times this whole quantity. So that's interesting. Interessante. Yeah. So notice what we have here. This is centripetal acceleration. This is acceleration due to gravity, and we're adding them together. Interesting. There's probably a lot to think about right there. Why that is. Why that should intuitively make sense. But anyway, let's go ahead and plug in our numbers, right? And this will give us the answer. So 60 kilograms times 9.8 plus the speed is 12 meters per second. So 12 squared divided by the radius, which is 30 meters. Wow, that's a pretty big radius, if I do say so myself. Okay. Let's calculate it. 60 times 9.8, 9.8 plus 144 over 30. Okay, so I'm getting, this is all right, yep. So I'm getting a force of 876 newtons coming from the seat applying to Josh. Interesting. And just to be clear, right, so his oh wait, you know what? We made a slight mistake here. we made a slight mistake. Let's look at this. FG, we know exactly how big FG would be. It would be 600 newtons. Oh, interesting. So according to the way we have it drawn, F normal should be smaller than FG, and yet, calculation-wise, I got a bigger answer. So we made a mistake here. I think the mistake was that we had these flip-flopped at the beginning. So in reality, it should have been FG minus FN. Oh man, I think that's what it was. Right? So let's make an easy fix of this. Plus, minus, minus, plus, minus, minus. Okay, interesting. If we multiply by -1 on both sides, then the way this will change, well, this will be a minus. We'll get positive, positive. Okay. Okay. And this will be a minus. Okay. I see. We need to adjust our answer here. This is where the real learning happens, friends. Okay. This is an answer that makes more sense, right? Our normal force we knew was supposed to be smaller. 300 newtons. Okay, that makes a lot more sense, right? So that would give us a net force of 300 newtons going in the downward direction, right? So that net force is the centripetal force that allows us to move on this circular path. Okay, good thing we caught that there. Awesome. So start with the free body diagram. If you know you're moving on a circle, set this up, right? That's always the next step. But as we just learned, make sure you have the appropriate signs, right? Because otherwise, if you get it flipped, you can get answers that don't make sense, right? So you want to, so I guess the way to tell if you have it flip-flopped or not is the centripetal force in this equation is acting as a magnitude, right? And being a magnitude, it should be positive. So yeah, I forgot this rule, right? Because notice, right, mass is positive, speed squared is positive, and radius is positive, right? So this is a totally positive quantity. But the way we originally had it written was giving us a negative quantity on the left side of that equation, which is inconsistent, right? Make sure you have a positive sort of difference in forces, right? When you subtract them from each other. Really important lesson. I'm glad we picked up on that. Okay, last question. This is actually one of my favorite questions. Y'all have maybe seen videos of this. I've never seen one of these in person. The closest I've come to it is the Simpsons movie where Homer Simpson drives on the dome trying to throw the bomb out of the dome. But the physics in that movie are absolute garbage, right? It just doesn't make any sense. But these right here do make sense, right? There's actually good physics behind this. So this is actually from the old textbook before this year, and I'm glad I snapped a picture of it. A motorcyclist in the globe of death, pictured here, rides in a 2.2 meter radius vertical loop. To keep control of the bike, the rider wants the normal force on his tires at the top of the loop to equal or exceed his and the bike's combined weight. To equal and exceed. Right, so what is the minimum speed at which the rider can take the loop? Okay. I know we have a picture here, but I definitely want to draw specifically the situation this is talking about, right? At the top of the loop, they want something very specific to happen. Right, so we have the bike. So I'll just draw him sort of upside down. Okay, there's my bike. It's good enough. Right. Where should we start? Glad you asked. Free body diagram, as always, right? So this last line is key. Rider wants the normal force on his tires at the top of the loop to equal or exceed the bike's and his combined weight. So he's got weight. So let's treat the man in the bike as one object, right? So he's got force of gravity for their combined weight, and then there's also a normal force pushing on those tires, right? And he wants that force to equal or exceed. And if we're talking about the minimum speed, then we're talking about the state in which that normal force is equal to, right? Equal to the force of gravity. Because you can imagine if the normal force is bigger, then he's going to have a greater centripetal acceleration, which would require a greater speed, right? And so we're trying to minimize that speed. The minimum would happen when those are equal. And the radius of the wheel of death, 2.2 meters. Cool. So now, what do? Well, set up your equation, right? Centripetal force equals the mass times the speed squared divided by the radius. So in this case, I have two forces that are adding together to create one big centripetal force. So that would be Fg plus Fn, which equals m. Do we have the mass? No, we don't. That's okay. So mass. Do we have the speed? Speed is what we're solving for. And then r, we have r. So mv squared over 2.2. Gravity in general, force of gravity is mg. Do we know the normal force? Well, we do. It's actually the same magnitude as the force of gravity. So actually, normal force is also mg. And so in this case, just like in a lot of cases, it actually doesn't matter what the mass is, right? Because if we add these together, we get 2mg equals mv squared over 2.2. And notice, yet again, mass cancels out. Has nothing to do with this minimum speed. We've seen that happen so many times. It's kind of magical how it always seems to happen. All right, so we have 2g times 2.2 is equal to v squared. And so it tells us that v is equal to the square root of 2g 2.2. So our minimum speed is approximately Desmos time, square root, 2 times 9.8 times 2.2. Square rooted, we get 6.57. 6.57 meters per second. So that seems fairly fast, not super fast. Wish I could convert this to miles per hour, but I want to say you basically double it to get miles per hour. So that would only be 12 miles per hour. That doesn't seem all that fast, but might as well look at the internet here. Let's see what the internet says. Maybe this is I'll do Chrome. Right, so Chrome. 6 meters per second in miles per hour. Okay, yeah, so 14.7 miles per hour. That doesn't seem very fast, but I guess, this is the minimum speed, so If you want to go faster, sure, go for it. But I guess it doesn't take that much speed to survive the globe of death. It's really interesting. So anyway, hope you enjoyed this. I hope centripetal motion is making a little bit more sense to you. I'll see you guys after the break. There should be some problems open in AP Classroom, maybe some also some daily videos I'm going to open for y'all. Remember, this is the only extra new content post test 2. So really test 3 is kind of a repeat of test 2 with the centripetal motion stuff in it. So anyway, take care, stay safe. Appreciate y'all.